Okay, we're back. We looked at how to describe the shape of a data distribution, and so now it's time to talk further about how to describe spread for data. So more on quantiles, box plots, and the standard deviation. Okay, so we looked at normal or skewed distributions. And so now how do we describe the shape? And this goes a little further. So it could be that all of our measurements are really, really close together with each other. So here, all of our measurements of heights are somewhere between 64 to 66 inches. So they're very close together. And then in contrast, here is a wider distribution, right? So this is running from a bit under 60 to maybe close to 70. We can see the difference here visually because of how I have created these histograms, but it would also be useful to come up with ways to describe these shapes quantitatively. So we can start out thinking about the median. And so as a reminder, so the median, if we identify where the median is, what that means is 50% of all the measurements are going to be below that line, and 50% of the measurements will be above that line. And so one method for describing the shape of a distribution is to describe it by its quartiles. So what do I mean by that? So quartiles will divide the data, kind of along the lines the median does, instead of into 2 equal parts, into 4 equal parts. So over here to the left of the median, we've got 2 quartiles. So the furthest left, the first quartile, contains a quarter of the data. The second quartile contains another quarter of the data, and so it comes right up to the median. Third quartile has another 25%, and then fourth quartile is the last 25%. So 4 equal parts. And notice that these lines are closer towards the median because there's more points packed in here. Okay, so quick question. So how much of the data are between the first and the third quartile? That's going to be half of the data, right? And this region is referred to as the interquartile range. And just because I love interrupting myself, I want to ask you a question here. Do you think back to the skinnier distribution that I showed you? How do you think the interquartile range is going to compare for that skinnier distribution relative to this wider distribution? So can that give us some indicator of the spread of the data? And having asked that question, now I'll turn it back over to you, Dr. Clark. And a histogram's one way to visualize both the center of the data and the spread, but they're really bulky. And so here's another way to visualize those characteristics for some data. That's with a box plot. So what I've done here is I've shown you transforming this histogram into a box plot. And so what you'll notice here is the median, and this box region is going to correspond to the interquartile range. And then I've got some whiskers and some points here on the outside. And I'll talk a little bit more about those momentarily. But the main point I want to make here is we usually display box plots on a vertical axis rather than a horizontal one. So if you want to visualize the histogram that this box plot corresponds to, you just got to turn your head sideways, and then you should be able to imagine the histogram. Okay, so let's now look at a box plot for the anorexia data. Okay, so box plot of the anorexia data, more compact. Okay, so there's a function for this. It is the box plot function. and I still like the color orange, so the first argument for the boxplot function is going to be indexing the column that I want from that data frame, so PREWT, the pre-weight data frame, and let's make it orange again. Okay, voila! So there's my compact display of that distribution. Okay, so let's talk a little bit more about the full anatomy of this box plot, and this may be a useful slide to copy or to print out. So we've got our median in the middle, and then we've got that first interquartile range inside of the box, right? So 50% of the data fit in that box. And then we've got a minimum and a maximum identified. And then there can be cases where there are some extreme values that are greater than 1.5 times bigger than the 75th percentile. So that's how outliers are identified. So these are extreme measurements, either extremely big or extremely small. So most of the data will be somewhere between these whiskers. Okay. So now, in the past, you may have generated bar plots when graphing data. And I am going to ban bar plots for scWriting. You might go back to bar plots after this class, but there are good reasons to avoid them. So we need to work with other types of plots for the time being. And the big reason why I'm going to ban them is because they're very deceptive. So what I'm showing you here are two very different distributions, right? So a skewed distribution on the left, symmetrical, quote-unquote, normal distribution on the right. But the means for both of these are really similar to each other, 1.3, basically. So if I graphed the means and made bar plots, these two graphs, I think you'd have a hard time distinguishing them from each other. They look very similar to each other, but these distributions are really different. And so box plots are a much more effective way of capturing the shape of the distribution. So if we look down here at these box plots, so here's the box plot for that asymmetrical distribution or skewed distribution. So median's down here. Most of the measurements are very small, and most of the measurements fit in between these whiskers. And in contrast, for the symmetrical distribution, that looks quite different, right? So the median's in a different location, and the whole distribution is in a different location. And so I hope you agree that these are much more informative than the bar plots that I just showed you. And you might have a question here whether you notice something else. Main thing I want you to be noticing is look at all of the outliers that are here for this skewed box plot. So that tells you there's something really different going on with this asymmetrical distribution compared to the symmetrical one. And another reason to use box plots is that it's a lot easier to visually compare groups with the box plots. So earlier, Dr. Burke introduced you to this anorexia data set, and she described how participants received one of 3 different treatments. So family therapy, cognitive behavioral therapy, or a control type of therapy. And we might be interested in knowing whether one of these types of therapies is more effective than the other types of therapies. So I could just plot scatter plots of these, but then I'm just going to be left kind of squinting at a bunch of points. And so, I might want to know out of these, is there one that has a higher measure of central tendency, or a higher center, or in other words, a higher mean, or higher median. So if I generate a box plot for these data, here's what I see instead. This tells a pretty different picture from these points, right? Pretty clearly, family therapy has a higher center compared to cognitive behavioral or the control treatment. Okay, so now how did I make that plot? It looks really great, right? Well, it turns out it only takes about 5 lines of code to make it. So let's go through and type out these lines of code and generate a beautiful box plot. Okay. So here we're going to go comparing the 3 treatments with a box plot. So you'll notice that in the slide I've included this earlier step to load the mass package. Since I've already loaded it, I don't need to repeat that. We can actually directly load the anorexia data using this data function. So now you'll notice that appears in my environment here. And the next thing I want to do is I need to calculate the change in mass from before to after treatment. So this next line here, what I'm going to do, I'm going to add a column to the anorexia data frame. So to do that, I'm going to use the square bracket indexing method. And I'm going to leave the row blank because I want this to be calculated across all of the rows. And I'm going to add a new column, and I'm going to call it mass change. Okay. And then I want to assign an equation to that column. So assign a calculation. So I'm going to use the concatenate function. And so if I want to get the change in mass, I need to start with the final weight. So I'm going to start with anorexia post weight, the final weight, and I'm going to subtract off anorexia pre-weight, the initial weight. Okay, so I'm going to run this line of code. And then if I go back and I look at the anorexia data frame again, it has added another column that is a calculation for my mass change, right? So here's someone who lost 0.5 pounds in this experiment. Okay. Then what I'm going to do now is a little cleanup step. Don't worry too much about this particular one at the moment, but it may come in handy later. And that is, I want to order the treatments in a specific order. So to do that, I'm going to index the treatment column, and I'm going to use the factor function. And this takes a couple of different arguments. So in this case, I'm going to apply it to the treatment column. And what I want to do is I want to specify the order of the levels within that factor. So the treatment groups within that factor. So I want family therapy first, cognitive behavioral therapy second, and I want the control third. Okay, so run that line of code. And now time to make my box plot. So for this, I will use the boxplot function. And what I'm going to do is I want to index, so I want to examine the mass change. And this function, the argument I need to provide is the y axis and then the x-axis. And then I'm going to basically be telling it y tilde x. And so then my x-axis is going to be the treatment. And so let's see what happens if I just run this line of code. Okay, so it's useful to run a minimal function and then start building out your function so that if something goes wrong, it's easier to catch where it's gone wrong. So now that I've determined, okay, I typed that in correctly, now I can start playing around with making the function look more pretty, or making the plot look more pretty. So now I'm going to go back and I'm going to add colors to each of the boxes. So I've just gone through and I've picked colors Orchid 1, light green, and light blue. Okay, and once again, I'm going to test and see if I added that correctly. Boom, I did. Okay, so now that I know I did that correctly, I'm also going to add on an x-axis title of treatment. Did I do that right? I did. Okay, then I'm going to add a y-axis label. Okay, and let's see if I did that right. Boom, I did. There's my plot. And now if I save this script, I can regenerate that plot in under a second. Okay, so that's your first plot in R. Okay, and you're still going to wind up encountering dynamite plots in the wild, so it will be useful to know how to read those as well. But just for the sake of illustration again, here again is that box plot I just created, and here is the equivalent dynamite plot. And I think if you take a look at these, you may be able to reach your own conclusion about which of these is more informative about the underlying data. But as you scrutinize this, you might discover you have another question also, which is, why do the error bars on this bar plot look different from the error bars on the box plot? And so we're going to talk about that in the next video.